Please welcome Adam and Duncan to S4 Stage 2.
Good afternoon. I'm actually Duncan Earl. Adam will be joining us later. This presentation is on quantum key distribution and its integration with ICS protocols. And as part of this presentation, we're actually going to tag team. So there's the first portion will be covered by myself. We'll be talking about quantum key distribution, the physics behind it, and some of our recent testing related to hardware, QKD hardware. And then I'll hand it over to Adam, who will talk more about its integration with something called SSP21, which is an ICS protocol. So with that said, this is a deep dive, so we have a chance to really explain what quantum key distribution is and why it could potentially be valuable to ICS systems. So I really am looking forward to the opportunity of explaining this technology, hopefully thoroughly, so that when you're done listening to this presentation, you understand how quantum key distribution works and how it can be valuable to you. Just as a very kind of top-level explanation, though, to start with, quantum key distribution is a new method for generating and securely distributing random keys to devices on a OT network. It has been around for, the basic idea has been around since the 1980s, and it was even studied by Albert Einstein in his early days. The thing that's different about quantum key distribution versus other key technologies is that it's not algorithm-based. It doesn't require, the security is not dependent on the mathematics and an adversary's computational power. It's based purely on physics, and as a result, it's a hardware solution and not a software solution. Ultimately, it produces keys that are truly random, that cannot be cracked, and you can guarantee the secure distribution of those keys to two parties that are wanting to communicate securely. It does this using entangled photons, which if you haven't heard about those, that's what the first part of this presentation will talk about. And it uses optical fibers to transmit these photons to two parties that are wanting to communicate securely. The advantage of entangled photons, as we'll discuss later, is you cannot intercept them or clone them, and so you can guarantee that only the two parties communicating have the secret key and no one else. This physics of entanglement is kind of strange, so I'm just going to give you a heads up. It's a little bit weird, and when we get to it, there may be some puzzling aspects of it. This is what Einstein wrestled with during his life. He called it spooky action at a distance, and we still have some of those same challenges and questions today. So hopefully we'll have a better understanding of what Albert Einstein meant when he called entanglement spooky action at a distance. So before we can talk about any of this, we have to talk about photons. And photons come in different colors and polarizations and all kinds of other features of a photon. But I don't want to make this too physicsy. So I'm just going to talk about a photon as being either happy or sad. That's really the only two properties that this photon can have. And in our work, we're going to want to study, or in this technology, we're going to need to focus on two aspects of photons. One of them is their randomness, and the other one is their correlations, which the next slide will touch on. So for quantum key distribution, although photons are a pretty common particle, there's billions of photons, pieces of light bouncing around right now on this stage. But for quantum key distribution, we want to focus just on one or two photons. We want to measure the properties, whether it's happy or sad, on just a single photon. So to do that, we have to use a new type of light source. And this light source, which we have some pictures of in a moment, starts with a crystal. There's a laser light, a pump beam that we run through the crystal. And that crystal produces photons from the laser light. And it produces them in a very sort of small amount. So it's a very, very weak light that emerges from the crystal. And so down here I've got a description showing these individual photons coming out of the crystal, and you can see that some are happy and some are sad. And one of the things I really want to hit on here is that that is random. How these single photons come out, what their properties are, is completely random. Even if I had the biggest computer and the world's greatest scientists, I would never be able to predict what the next photon's properties is going to be. So that's a really important factor when we're looking at security, because true randomness, something you can't predict, is going to be the cornerstone of this technology. So we use this process of a crystal to produce single photons, and they can have properties of being happy or sad. The second quick area we need to focus on is something called correlation. Sometimes we want to look at two photons at the same time. And there's really kind of four scenarios. Those two photons can be the same. They can be both happy or both sad, in which case we're going to call that perfectly correlated. Or they can be the exact opposite, one happy, one sad, and vice versa. In that case, they're anti-correlated. Correlations are also an important component of quantum key distribution. Okay, so that's the background that's needed to actually understand entanglement. And we're going to do things a little bit different to produce entangled photons, but here's the basic gist of it. We start with a crystal that's made in just the right way, and a pump laser that's focused in just the right way. Then instead of getting single photons produced, we actually get pairs. We get two photons, twin photons, produced at the same time. And these pairs are created inside the crystal at exactly the same time and at exactly the same point in the crystal. And so the result is that they share a special bond. You can kind of think of them as twins that are being produced together. In fact, this photo down here in the lower left is an example of what an entangled photon source looks like. And as you can see, it's fairly small. We have smaller ones now that fit on printed circuit boards. So this technology has been developing for 80 years, but it's now starting to be a commercial product. So the photons, the entangled photons that are being produced, come out in pairs. And in this case, I've shown them as having a certain value. They're perfectly correlated, and I show them coming out in a series. That's a little bit of a misnomer. They actually have an undefined value, which we'll look at in a moment. Okay, so what can we do with these entangled photons, and why are they special? And how can they actually help us with encryption or authentication? So the really important thing about entangled photons is that they have, they're correlated in a way that depends. It depends on how you measure them. So if you imagine this entangled photon source producing these pairs of photons, if I measure them in one basis, I'm going to get one type of correlation. If I measure them in a different basis or a different reference frame, I'm going to get a different correlation. And let me sort of unpack that statement. So if you look on the top, I have some entangled photon pairs that are being viewed through an observer that's in kind of the straight up and down. We call it the 0-degree reference frame, and you see his sunglasses. When he looks at those two photons, he sees that they are perfectly correlated. And he doesn't know what he's going to get, whether they're going to be too happy or too sad. That part is random. But he knows that in the 0-degree basis or reference frame, the correlation is perfect. They always are the same. However, if that same observer had tilted his head 45 degrees and observed those exact same photons, then he would have found that they would be anti-correlated. You'd have a happy and a sad, then they would always be different. And again, it would be random. He wouldn't know which one would be happy and which one would be sad, but he would know that they would be always different. So that's actually kind of a profound thing. There's no other particle that can do that. The correlation between these two particles depends on how you measure it. And that is what entanglement is. So how do we use that for a quantum key distribution? One thing you can think about with these two photons is this correlation, the special bond between these two photons. It persists if they're next to each other, and it also persists if they're very, very far away. So if I take a pair and I split them, and I send one to Jupiter and the other one to Venus, even though they're far away, they're still going to have these same correlations. If both parties, one on Venus and one on Jupiter, choose the 0-degree reference frame, they're always going to get the same property, always happy, always sad. And if they choose the 45, they always get different. So maybe let me just pause there for a minute and think about what that means. How does the photon know when it leaves the crystal that it's going to be measured in the 45-degree basis or the 0-degree basis? it doesn't, right? That's something that's going to happen in the future. So how does it know that it needs to both be happy or both be sad? There's no way when these two photons are created for them to know what's going to happen in the future and know how they need to be correlated. Unfortunately, this effect happens instantaneously. So even if they're many light years apart, you still get the same correlations immediately. So there's no way for them to quickly communicate with each other and say, hey, I was just measured in this reference frame, so you should switch to happy or sad. There's no way for them to communicate that quickly, since you can't communicate faster than the speed of light. So there is this strange quantum bond between these two particles that allow them to be random yet correlated even over great distances. And that is a really powerful phenomenon that we can use for cryptography. So here's how a quantum key distribution system works, given all that background physics. We have in the middle, we have a quantum key distribution transmitter, which is just an entangled photon source. And you can see that that source is splitting the two entangled photons, sending one to the left to a receiver and the other one to the right to a receiver. And each of these receivers is going to be making a measurement on the photons that they received. I show each photon as not being happy or sad because I don't really know what it is until we measure it. So it's just kind of left as being both, or simultaneously both at the same time. So to see how quantum key distribution works, you can imagine the first receiver, the one on the left, he receives a photon. He would say to the other receiver, hey, I just received a photon. I measured it in the 0 reference frame, the 0-degree reference frame. I'm not going to tell you what I measured, but I did just now measure a photon. And the other receiver would say, oh, I got a photon too. Those must be a pair. I also measured it in the 0-degree reference frame. And so I'm not going to tell you what I measured, but I now know what you have. Because we both measured them in the 0-degree reference frame, they must be perfectly correlated. And now both receivers know what the other person has as a photon value or as a measurement. And they never need to disclose this. The only thing they need to disclose is what reference frame they used in the measurement. At this point, these two receivers now have one shared secret bit. It's purely random. No one else knows it but the two of them. And it's a shared secret bit that could ultimately be the start of a longer key. They do this process over and over, and eventually they end up with 256 random bits that they share, and that's the start of the QKD key at that point. So there are some possibilities where they choose different bases and they actually get just nonsense. They can throw that part out. It's only when they choose either the 0 or the 45 degree, when they both choose that they get correlated data that they can interpret or infer from the other. So this technique is probably different from public key infrastructure and other mathematical-based encryption solutions you're probably familiar with. And in the 1980s, it was demonstrated experimentally, but it was a laboratory that was almost as big as this room. I mean, there was a lot of optics equipment to make that happen. Fortunately, over the last 30 years, we've shrunk that down considerably, and now we have rack-mounted systems that can do quantum key distribution. My company, Cubitek, makes a system, but there are other companies in the world that do it as well. We're the only one that use these entanglement-based entanglement-based photons, though, and we are the only company that's focused on ICS. And I'll tell you why we're focused on ICS, and specifically the electrical grid. So you can learn more about the specs on this system, but I'm going to skip over most of the product information. So the advantages of a QKD system to an OT network is that you really simplify your operations. A lot of the public key infrastructure for some applications can go away. You don't have to deal with key revocation and some other complex sort of maintenance efforts that is typical with other keys. And for some applications, like with the electrical grid, you have operators that are already a little wary about having cybersecurity on their critical signals. This is a very hardware-based, kind of transparent solution that in many ways is appealing. It seems like it is a very low interference type approach to encryption. You can use the keys with AES 256 or with one-time pads. However you want to use it ultimately is up to the user. All the QKD system does is provide and distribute these purely random keys. And Adam will talk more about how we're actually taking these keys and doing things with them. There's a number of other advantages. You don't have a centralized storage of keys. If you're worried about quantum computers coming and cracking the underlying cryptography of your systems, that goes away here. A quantum computer can't do anything to this system since it's not mathematically based. So it simplifies life, and it also eliminates some critical vulnerabilities. One of the other really big advantages of the system is that if anyone ever tries to eavesdrop on a communication channel, you can immediately detect that and shut down the communications. So it's a way to guarantee that your channels are secure as well. So those are the advantages of QKD to industrial control systems, but I'd like to flip that and talk about the advantages of industrial control systems to QKD. QKD systems have been evaluated for financial organizations, for IT networks, and really they've had a difficult time getting any type of market traction. ICS, particularly electrical or utility-based networks, are really a good fit for quantum key distribution. A lot of times there's already dark fiber, optical fiber that's in the ground that we would leverage in implementing a QKD system. Plus, the distance traveled between communication points is often not very long, which is a limiter for this technology. And the key rates, or the data transmission rates, are low compared to other applications. So it's a really nice complement to the limitations of QKD technology today. And of course, the low hassle key maintenance is a pull or a draw from some of these different applications. So today at San Diego Gas and Electric, as part of a DOE-funded project and a CES 21 funded effort, we have a demonstration system at San Diego Gas and Electric's integrated testing facility. This is a shot of it. We not only do we have a quantum key distribution system set up and being tested in a lab, but we have tools to try and hack it, which you really can't do. Any attempt to intercept one of these entangled photons breaks the entanglement bond and is immediately detectable, but we can still run some scenarios with this system at ITF. And our goal ultimately is to demonstrate using QKD to secure SCADA communications between substations. So if you have a control center and a substation and you're wanting to securely talk to your SCADA, the plan is to use QKD keys that have been securely distributed with something called the SSP21 protocol to help make that happen. So again, QKD, it distributes the keys using physics. Once you get the keys, though, you have to do something with them. And with that, I'll turn it over to Adam.
So, a lot of QKD applications to date have been really concerned with the key distribution rates. Because if you're DoD and you're trying to talk from military base A to military base B, a lot of those applications may want to do encryption just using one-time pads and get the absolute theoretical maximum security possible out of the technology. Since we're securing SCADA protocols, where encryption isn't so important, and we're really looking for authentication and integrity, we took kind of a more practical approach and decided, well, we already have this effort going on with SSP21, and it does public key modes, that we would just kind of extend that protocol to support shared secrets and to support these sort of ephemeral or one-time shared secrets. So the first couple slides here will be just a little bit of a review of SSP21 so that we get the proper context. We presented this in much more detail at S4 last year. But we'll just go through a couple of things. The SSP21's handshake starts out with a request and response that performs key agreement. So after your master sends this begin handshake request to the outstation, and the outstation replies with begin handshake reply, the two will have a pair of session keys for transmitting messages in each direction. They will only agree if they're the parties that they claim to be. But at this point, you haven't actually performed authentication. So the next two messages are an authentication message that can also kind of optionally transfer data. And this is a little difference, a change that we made since S4 last year. to the specifications, so we can get down to what's effectively kind of a one round-trip handshake, because those two authentication messages can actually kind of go ahead and payload some of that, layer 7 application data. But the devil is in the details for how the key agreement is actually performed. So we have 4 modes in the protocol. I think at S4 last year we had a pre-shared public key mode, kind of like you would use PGP email. Everybody knows everybody's public keys from a key server or somehow out of band. Then we had certificates where you could root trust with an authority, and that's what we talked about last year. Since then, we've added 2 new modes. One is a shared secret mode for deeply embedded systems where you have to put the same secret in both sides because perhaps the processors can only do symmetric cryptography. And that mode was similar enough to the QKD mode that we kind of used that to bootstrap for the QKD mode. And so we'll be talking about kind of how those 2 modes work. So this is key agreement if you have a static shared secret that kind of lives for a long time. And at begin handshake request, the most important field is a random nonce sent from the initiator, and both sides hash that whole initial message and save that to a value H. And then the responder, which would typically be an outstation or a remote field asset, sends back his random nonce. And at the end of this, they both have a hash that will only agree if someone hasn't tampered with the 2 messages to keep that running hash. So then we feed that hash as the salt parameter into a key derivation function, and then the secret input key material, or at least partially secret, is the long-lived shared secret with the 2 nonces sort of appended to it. And that's how we can kind of keep using that long-term shared secret for multiple sessions. And then once we have those 2 session keys, S1 and S2, we kind of use them like we would for any other protocol. We use that to secure a session that might last an hour or until we sent a certain number of messages, sort of the way TLS or any other protocol works. The point here is that H protects the messages from tampering, and the calculation is kind of the same on both sides. So key agreement from QKD is actually even simpler. So one of the message fields here we kind of repurpose to be a key identifier. The initiator says to the remote side, hey, I want to start a session, and let's use this key, and we send a key identifier. We haven't actually standardized what that key identifier is. We've kind of played with 2 different modes. Duncan's system supplies like a very large incrementing counter as part of the QKD key distribution. So we get 1, 2, 3, all the way up to a 64-bit, 128-bit integer. We can use that as an identifier. Another option would be, say, a secure hash or fingerprint of the key. We don't actually reveal the key, but we say, the key has this identifier. The other side really doesn't have to say anything back other than, okay, I've got that key. They do the key derivation using the secrets. The only difference here is that we don't need any entropy at all from the device, because we're only going to use this key for 1 session. So we don't even need a random number generator on the device, which is a huge win for embedded systems, because we all know, people have done reverse engineering, we all know how those can flake out or not perform as they're designed to be. But really, the handshake is really the same. We still have the same properties. H protects all the other parameters in the handshake, because we have to send other things. We have to say, well, is this going to be an encrypted session or an authenticated only session? How long should the session live? There's a whole bunch of other parameters in those initial messages that kind of get protected. Some of the key insights to this handshake are, though, that this is only symmetric cryptographic algorithms. There's no public key cryptography in here. So even if someone gets a quantum computer, they're only going to reduce our key space from 256 bits down to 128 bits. We're still secure, even though, because fundamentally this mode, the only cryptographic primitive is a hash function. Just one hash function, and we use that for HMAC, we use it for the key derivation function, we use it for everything. So by design, the QKD mode is very, very simple. So here's what we actually did in the lab. You saw the sort of picture that Duncan had of the rack mount, and this is more of a block diagram. So our goal was to secure DNP3 communications from a SCADA master to an outstation. And as part of our open source effort for SSP21, we've developed a proxy that, it acts just like a TLS proxy. It takes insecure traffic, it wraps it in the protocol, it ships it to the other side, and which unwraps it. But instead of having to configure those properties with static keys, we get the keys from the receiver. And we had long discussions of, what cutting edge, communications technologies we would use to tie the QKD receivers to the proxies. Yeah, we used RS-232, 8 and on 1. So totally insecure, but you have to understand that in the long term, that QK receiver is probably going to be inside the equipment. So for laboratory purposes, that's how we did the integration. So the long-term vision is, of course, to be much more tightly integrated. You'd have the QKD receiver living inside the remote device. The QKD transmitter, at least for a SCADA control center to substation, would probably live up in the control center. It doesn't have to be right next to the master, but for serviceability or any other issues, it would probably live there in the control center. So that system is there. It's working. We've done some initial testing. There's quite a few questions I'm personally interested in. I mean, I view QKD as more of something you have instead of something that you know. So if you think about it, I mean, if someone has another QKD receiver, they could just pop the optical cable out and plug in, right? And they could be then the source of truth, right? There's no other way of securing that type of a system. So there's possibility there that you can sort of hybridize the schemes. Possibly in that key derivation function, use a more classical cryptography combined and bolstered with the quantum keys. So almost like you do two-factor authentication, it can be kind of what you know and what you have. Would be something interesting to explore. And I know that Duncan's company and SDG would like to get to some type of a field pilot where they're doing this demonstration they have in the lab on an actual system over larger distances. But I think that this is a mode that we are going to push to standardize in the SSP21 protocol, even though it is kind of forward-looking. Maybe 4 or 5 years out before people are actually installing these things, but we kind of want to have this capability in the protocol. So if you don't have dark fiber, you don't have these things, well, you can use the more classical modes in SSP21. You don't have to pick one key management style for your entire system. So I'm hoping there's lots of questions, and I think we have 8 minutes left, so let's invite Duncan back up here and we'll take some questions.
Equivalent, if you will, so we could use other type of cable to transmit the same characteristic, if you will, and not have to do fiber.
Well, the thing you have to realize is as soon as you turn those entangled photons into bits, they're just as vulnerable as any other key. Yeah. So you want to do it as close to the place you're going to consume them as possible.
There have been some satellite beamed versions of QKD that are out there, and there's free space as well, like between buildings. So there are some other technologies that get the photons, for further distances into more remote places. But yeah, you're absolutely right. I mean, ultimately, you can't convert it out of a photon, or you lose that entanglement property.
So I have no way to represent light electronically yet?
You turn it into electrons, but then you lose that entanglement in the process. Sorry.
I think one thing that's in the slides that we didn't cover is, Duncan's company and others are looking so that you don't have to have parallel infrastructure. You can have the classical communications and the photons sharing the same cabling.
And one of the things that's exciting about the electrical grid space is there's, utilities, many utilities across the United States that have a lot of dark fiber. So you could imagine that network coming together, and it doesn't have to be dark, as you're pointing out. It could be the lit fiber as well. But there's actually quite a lot of fiber optic resource across the U.S. that could be utilized.
Yeah, I had a follow-up question on that the same idea. Was you need this fiber everywhere, and that's a huge barrier that's going to eliminate probably about 99% of the applications where people are using the public internet because it's a public internet. They don't want to use their own private network. Yeah. Does this mean that quantum cryptography is going to be fundamentally limited moving forward, or is this just happens to be your implementation that you've been able to build?
So just to quickly answer that from my standpoint, the fiber is definitely a challenge, and that creates niche applications for us, which is where we're focused at right now. However, there are some other kind of hybrid solutions, basically like a depot where you get keys and then you distribute them through other processes. There's other kind of hybrid solutions to try and get around the fiber requirement. Having said that, our belief is there is critical infrastructure applications where this technology makes sense and there is fiber available to support it. But again, as the technology matures, I'm sure you'll see some hybrid solutions as well. But that is one nice thing about SSP21 is you do have a protocol that can work with any of them. I mean, if you've got the fibers and you can do QKD, then you can leverage SSP21 for more secure communications. But in places where you don't have it, you can drop back to public key approaches.
All right, and that literally was going to be my next question, is ICCP between control centers. Is this another potential target for wrapping via SSP?
Using QKD?
Or using QKD or one of the other modes that you put together?
Well, I mean, absolutely. I mean, you could use TLS if you're talking from system to system. So for ICCP, many of the benefits of SSP 21 aren't as salient when you start talking about organization to organization. But you could.
I have a question regarding the distance. You said 20 kilometers is the limit. Is there a way to extend that a bit? Because so I'm from Europe, as you probably can hear. 20 kilometers is even in Europe nothing for a substation to a control center communication. So
it all goes with bit rate. So if you're okay with less key bit rate, then you can go further distances. So there are QKD systems doing up to 400 kilometers now. So, but again, your bit rate goes way down.
And this particular integration requires a bit rate of 256 bits per hour, because we consume one key and then we use that for an extended session that might last for an hour. So we don't need high bit rates with this particular integration.
Yeah, I think the 20 kilometer was like 20 kilobits per second, something in that range.
Orders of magnitude more than we need for this.
Absolutely.
Yep.
So Adam, later on, aren't you in a discussion on the main stage to discuss TLS versus SSP 21?
Looking forward to it. Was that a question?
It was a plug.
Little advertising.
No, Mike kind of stole my question, but I was looking for other applications. I'm thinking, especially in the region you're in, the WAN, for example, the NASP efforts that are going on what used to be WISP. So we're looking at things like the synchrophaser projects. But it gets back to the distance issue. How do we expand that length so we can use and Adam, can you speak more about the potential for multi-entity use of this?
I mean, if it's multi-entities, somebody has to own the transmitter, which is a bit of a sticking point, right? As far as SSP 21 goes, we have a full, PKI mode. I mean, it's certificate-based, certificates that are purpose-built for SSP 21. Right, I think that would be diverging from the point of this talk a little bit.
Well, we are, for the QKD systems, we are going to what we call a transceiver model, which is you have your receiver and your transmitter all in one. So you can have one transceiver, another transceiver, another one, and you can kind of just daisy chain them on.
So each entity could be both the transmitter and receiver and share the duty
That's
of
exactly
key
right.
generation.
So you can really build, you can scale up and build a network. Of course, SSP 21's got to handle the synchronization of all that, which we haven't worked out. But that's the more longer-term, greater distance, larger network solution, I think.